Okay, so I hope you guys read that little theorem. We had two important theorems in this. One of them told us how to do what?
Squeeze.
One of them was the squeeze theorem. That's the one you're supposed to read about a little bit, right? What's the squeeze theorem tell you? Can you give me a little bit?
If you have three functions and one of them squeezes between two of the other two touching, then you're able to find that point using the other functions.
What's it allow you to find? What's the punchline? You explained the setup well.
Allows you to find the point of intersection.
Allows you to find the limit
Yeah.
of the function that is in the middle if you know the limit of the things that are on the top and bottom, right? The catch is that thing that's in the middle has to be in the middle everywhere.
Yeah.
That's how you get it. It's got to be squeezed in between those other ones everywhere. So I'm going to show you another example that I think really illustrates this, that I think is a nice example. The proof of it
Really
is
confusing.
pretty difficult. I mean, that's a pretty difficult proof because this is a big theorem. Like the squeeze theorem is a big piece of machinery. It's an important, huge piece of machinery that has a difficult proof with it. That doesn't mean that's the only proof, by the way, but that's our book's proof. And I like it. It's just difficult. Okay, so we need the squeeze theorem to do certain limits. By the way, the squeeze theorem comes back in Calc 2. It's this really important thing, and I love it. It's just, it gets you to take sequences that like are above and below, and you can squeeze your sequence in the middle and just do some really cool squeezy stuff. Okay, so let's see another example that I think really shows it well. This is like a Calc 2 type example almost. It's not with a sequence, but it's close. Let's look at it. So let's say we wanted to do this limit. Now what the squeeze theorem says, let's see if I can remember it well enough, okay? So we need, this is an important one to read. It says if you have three functions, so let's say we have h, f, and g, we'll say that h is the small one, f is in the middle, and g is the one on top. It says that if that's true for all, I'll give you guys even the symbol.
If and only if.
For all, that's for all x values, and I don't know how the book says it, but in the neighborhood of x equals c, then, punchline, what can we do? We can say that, oh wait, I need more stuff. No punchline yet. Sorry. And, so we need more stuff, more hypotheses, and the limit as x approaches that specific c of h is something, so we get a number like 3 or 2.3 or something like that. And the other limit for the thing that is on top is also that same thing. This seems like a very specialized circumstance, right? But it turns out you can often do this. You can often find something on top, something on bottom, smash something else in the middle, and find the limit of those two and show that it's the same as the other limit. So the punchline is the limit which you were trying to find of f is the same thing. Okay? So that's the squeeze theorem. I love this stuff. It's squeezy. This limit right here. I think that if we tried to do this right now, it'd be difficult. Let's see why. If you just plug in right away, you get that, what happens in there?
Earth is defined.
You have like undefined inside the sign, so is plugging in gonna work?
Not well.
I don't think so. That's totally wrong. How do you, what's undefined in the sign like that? That doesn't make sense. Doesn't compute, okay? So then you say, well, maybe I can use those limit rules we learned like this, right? We had limit rules that said you could break this up to be a product. Like that, right? Just a simple limit rule. And then the first limit, what's that come out to? 0, but once again, what happens there?
We start having issues.
Dang it. That didn't work either.
Wow, we should just quit. Just kidding.
Well, if you didn't have this squeeze theorem, you would. You'd just be stuck. So, this sine of 1 over x thing, do you guys remember what kind of shape that had?
Oscillation.
It's an oscillating thing. That's why the limit's having issues. Remember, that's one of those 3 ways a limit can have issues. If you think about the picture of sine of 1 over x, it looks like this, right? Negative 1. One there.
Opposite day.
Oh, it's hard to draw these darn oscillating functions. I'm just going to pretend this. Okay, there's what the sine of 1 over x looks like approximately, right? Even though we can't find its limit as x approaches 0, you guys agree with me? The limit as x approaches 0 of this doesn't work because, again, oscillating. The other 2 ways the limit could not exist are jumps and asymptotes, right? But even though we can't do that limit, can we say this? This is the key, and this is a very key Calc 2 argument. That function, even though we don't know exactly what the limit as x approaches 0 is it trapped? It's trapped between what?
1 and 8.
So can you write this inequality and say that it's true for all x values? Is that ever going to go outside of 1 to negative 1?
No.
It's not, right? So that's true for all x values, right? Why am I saying for all x values? Okay, getting there. Now, do you guys agree that I could just multiply through this by anything, as long as I do it to every side? That's the fundamental rule of algebra.
Yes,
Yeah.
I do.
So I'm going to multiply through by x squared.
Can you multiply by anything? What? Oh.
So
Okay.
here's some O's. I like that. Okay. So do we agree that's true? I didn't do anything fancy. I did algebra 1. I multiplied through by x squared. Every side. That's allowed. You can do anything as long as you do it to all sides, right? So that's true since that was true, and this is true for all x values since that was true for all x values. You agree? Okay.
So you find the limit as it's approaching x squared and no.
This satisfies that hypothesis then. Do we agree that this is like
Yeah.
this is like this? We just said it was true for all x values by looking at the picture and thinking about it a little bit, right? So now, if we can find the limit of h and we can find the limit of g, guess what? That other one has to be squeezed in there. This is awesome stuff, right? So the limit of this as x approaches 0, and we stick a limit on here. So now we're going to limit all 3 parts. The limit of this guy as x approaches 0 of negative x squared, what is that?
0.
0, obviously. The limit as x approaches 0 of the right-hand side, x squared, is just
0.
0. So since those are both equal to the same limit, automatically the thing that's squished in between them has to also have a limit of
0.
0.
I have a question.
As a picture, hold on, and I'll answer that question. Okay, I'm too excited, you can't stop me.
I'm sorry.
No, we'll definitely get to your question. But as a picture, that is just the sine of 1 over x. What's x squared sine of 1 over x look like? Well, it turns out it's also got an oscillation thing that's happening, but its oscillation is trapped between x squared and negative x squared. These are like the asymptotes.
At 0.
Those aren't the function. The function is trapped between those, and it's going like this, oscillating, oscillating, oscillating. What's different about this oscillation from the other one? That one goes back, bouncing back and forth. You can't
It
decide
has
its
to go
limit.
through like a funnel.
Yeah, exactly. It's going through the squeeze. This guy, do you think that it actually has a limit? As you get close to 0, arbitrarily close to 0, what's it getting close to? Y equals 0, too. That one, as you get arbitrarily close to 0,
Well, you're
you
still.
can't decide. See what I'm saying?
Don't tell me to ask him.
You guys like that example? I love that example.
What is that graph?
What?
What graph is that? Is it the x squared?
This is actually, this blue right here is x squared sine of 1 over x. You can put it in your calculator if you want to see it.
How can you fit anything between x squared
What's the
and
proper
negative x
terms of
squared?
verification?
I'm saying that oscillation.
How can you fit anything like way
Yeah.
deep inside there?
Yeah.
You can.
You can? How?
We just did it.
They get so close to each other that they're practically the same point.
Oh,
Think of it
okay.
like that. That's
Okay,
fine.
yeah.
That's an
That
okay way to
helps.
think about it. But did you agree with like my different steps there? This is trapped between -1 and 1, right, Kyle?
Yeah.
So then I can multiply through by x squared, and then I can use the squeeze theorem to say that that's true. Like, it works. Strange though, right? We're gonna see strange wacky ideas. That's cool. All right. Why do we need the squeeze theorem? Well, problems like that. Let's see a couple other real common problems that you need this kind of thing on.
Are you gonna go over the bottom the part of this?
I'm not, Austin, because
Okay.
it's a good question though. Did you have another one on this?
No.
It was just that?
No, I answered my own question.
Did you?
Yeah, but that's another question I have. If you're going over the bottom.
I'm not going to. I mean, it would take us too long. We could, but can I have this for just a second?
Yep.
I'll make sure I don't remember one incorrectly. So there's two special limits. These you need to memorize.
Yeah.
Wait, Miss McGee, another way, could you, if you just put that in your calculator, couldn't you find like the, the minimum or maximum? And wouldn't that give you the same
Of what?
of the, like right there, like you see how they're like parabolas?
Yeah.
If you found the minimum or maximum, wouldn't that give you the same point? Like,
Yeah. I mean, you could look at this picture and evaluate the limit with the picture, right? You could say, oh, it looks like it's getting close to 0, so the limit is 0. You could. But this provides you an analytical way to do that without the picture. We didn't have pictures like this that were so nice until like, the last 20 years. So how'd they do it before that? Well, this was done back in the 1800s. And also, sometimes the picture is too crazy, like you won't even be able to look at it, but you can apply this. So that's a good question. I like that question. That's why in this class we have to do graphical and analytical. Huh?
I would have hated to be a mathematician like before.
Yeah, it is nice technology.
I can't
I'm an applied mathematician, so I like the technology.
I can't imagine.
I like both though. I like all math.
See,
The person
I like
who
the
programmed the
analytical side,
calculator.
so I
All
don't know if I
higher
would
level
have
math
liked it
classes
that
are just
much.
fun. It's just,
Like, Miss
it's
McGee,
just,
how do you program a calculator? That sounds like the hardest job in the history of mankind.
No, it's not.
Programming calculator.
Programming stuff isn't that bad. I just erased this, sorry.
It's like, I made that guy.
Okay, enough tangents. We had a lot of fun, but I did. Okay, these are two special limits. You got to remember these. Where'd they come from? That proof that Austin's talking about on the bottom of the page shows where one of them came from. Okay, it gives you a proof of where it came from, and it uses its key step in the proof is the squeeze theorem. So these are true by the squeeze theorem. There's no other way to come up with these limits. There, we're done with the squeeze theorem. So if you have sine of x over x and you approach 0, it's 1. If you have 1 minus cosine of x over x and you approach 0, it's 0. So these were both done with the squeeze theorem. If you know these, that'll allow you to do a bunch of other kinds of similar limits.
Because they're identities.
Yeah, these are identities, limit identities, exactly. I like that, thank you. So here's an example of something you might need this for. And like, for instance, these would be things that they might put on a calc problem on the test. Like I said, they don't have a lot of limit problems on the AP test, but it would be very easy for them to put one of these on there, and they're not going to give you the formula, you need to know it. Just like they're not going to give you formulas for derivatives, you're going to know it. Okay, so how can I change that into something that I can do?
You can pull the x out of the bottom. Or you can separate it to 2.
I can kind of separate it out. Let's try to take it apart. She's trying to take it apart. I can always take this 1/2 out, right?
Yeah.
That 1/2 can just come out way in front. So I did it like this. I pulled the 1/2 out, then I split them into 2, like Caitlin's saying. How might you split that? Anybody got an idea?
Sine over x times 1 minus cosine over x.
So we could go like this. Let's do this limit. And then the second part.
Wait.
What do we have left? We took care of one of those x's and the sine. So we have that whole 1 minus cosine left over, still got another x left. And then those are both identities. So this is 1/2 times 1 times 0, so the overall limit is 0. Okay? So it's really just using identities here. Good work. Let me see, I had one other example I want to show you if we're good. So this one, I remember doing these in Calc 1 and 2 actually. Seemed to be a popular problem at my university at least. So how can you do that?
pull out an X. Just kidding, you can't.
Compare.
If you wish.
It's just sine of x of x over 4.
There's just a 4.
Is it
We need a 4, right? Where do we need a 4?
And it's,
Multiply.
If this was 4x down here, would we have a problem? Because then it'd be like 4x over 4x, and I think we could still say that. But
multiply by 1/4.
can you just arbitrarily multiply something by 1/4?
Do a clever formal.
Ah!
That's what I was looking for.
So multiply by, you want a 4 here.
4 on top.
Yeah,
I better put a 4 there too. That's 4 over 4, right?
Oh, I'm gonna have to erase.
Guys got it so much easier than people did last year.
4 over 4? Is that what you said?
Why did I put a 4 there and a 4 there? That looks funny, right?
Because it's still, because that's like on the top. It's like 4 over.
I can just go like that, right? And limits allow you to pass things inside and outside. Constant values, not variables, but constants, can go inside or outside of them. So if I multiply by that, this can go down there as 1/4. We agree with that? And that helps us because now we've got 4 times the limit as x approaches 0. And let's just think of this
wouldn't
as,
it be
hold
4
on,
times 4?
as the sine of u over u.
Yeah.
U is what? 4x.
Yeah.
But this says the sine of anything over anything. If you have that situation, you can use the identity and say that
that's
that part
1.
is 1. So it's really just 4 times 1. So that's 4. So you can fix up a limit that has that issue. But multiplying by clever
Which
1.
of these are you using?
Those two right there.
Okay.
New identities. Proven by the squeeze theorem.
Okay.
And I would have gone over how to prove one of these with the squeeze theorem, but if you look at the book, you'll see that that's a little bit involved. We don't need to see that. That's why I showed you that other one was easier. Questions? I think we're good. I guess for the rest of the hour, so hope we can get it done.
I'm hoping so too.
I have a question on
Yeah,
54.
number 50.